Good morning, everyone. Welcome to another episode of XA Talk Show. Let me get prepared while I wait for people to come on. And today we're gonna talk about lots of things. So I have the XA Talk Show webpage. Yesterday we did a keyboard session all about keyboards. So I need to do that. And today's topic, I might talk about mathematics. Well, not mathematics, but why LaTeX sucks. And on math notations, on the history of math notations, and its relation to formal systems, and what's an alternative, things like that. Hey guys, Olari and Isaac. So, you guys know the format. You ask me questions and I answer. So let me type your questions here. Or when I'm talking, just comment. Put your opinions. If you have a question, ask me questions and whatever. That's uh, that's a current situation for the XA Talk Show. So what I'm going to do now is to put the topics here in the YouTube panel. First of all, type questions, uh, comments, your opinions. Act you as I talk. So that is the situation. So this is XA Talk Show in today's date, and let's go back to. So let's get the title and everything correct. So there, you should see the list of topics. Hi Olari, dies. Interesting topics. Looking forward to this one. Cool. Uh, so um, let's close that. Let's go back to my Emacs. And while I'm in Emacs, let's turn on. Let me show you this. So I've showed this many times, but in case anyone is new, I think you guys are new here, and it's XA start command log. Now, if you are an Emacs user, this mod is great because it records every command call, on the left panel. So if you are wondering what command I just called, you can just see the command there and search the web. You'll find it. And meanwhile, let me drag this over here a little bit so that it's not hidden. Okay, so I think yesterday Break the Loop asked me a question about math notations. Math notations. I have this article about tech pestilence. Sorry, tech pestilence, or just tech sucks. Search for why tech sucks. Tech is a very popular, extremely popular among the hacker types of programmers. Like they are gonna say tech and LaTeX. Tech. So tech is the package created by Donald Knuth. Uh, does by the way, does anyone know how he pronounces his name? Is Knuth or Knuth? Donald Knuth. Anyway, he wrote. So if you know, type it. He wrote a series of books on the art of computer programming. Was it art of programming? The art of programming. Yeah, I think that's a title. And it's supposed to be like 9 volumes, and it's still unfinished. Right now, it only has like 3 volumes came out, and fourth volume. Knuth. Okay, Knuth. Hey, Break the Loop. Great to see you. So I'm gonna talk about the why LaTeX sucks and what's an alternative. Now, if I missed, if I didn't, if you have something like, if I didn't address your question, if you have something you want to know, just remind me. I mean, you know, I, you know, I, yeah, just feel free to type anything. I tend to come across, like, I noticed my friends, I tend to come across as FOMO, like whenever the people, like they start to, I mean, it's like two extremes. A lot of people just consider me as a troll, whenever, like, still there are people, whenever they see my name, without my involvement on the hacker news and elsewhere. I know some of these people, I mean, I know their names. Whenever they see someone mentioned, my article or my name, they'll just come in and post, that guy don't know shit. That guy is crap. So it's on one hand, it's like that. Then some people who follow me on Twitter, some like I noticed that they start to when they talk to me, they start to be very super polite and formal. It's like, thank you very much for your great work, and very polite, and that's great, but that's not. It's not. I guess the reason it's that way is just because my personality came across that way. Because I tend to be, I tend to be this ascetic, guy who is, concerned about morality and concerned about the world of affairs, analysis of all the situations. But you don't have to be that way. You be, whoever you are. That's the best. It's like sometimes, I haven't talked to. I'm not much of a social person, so it's almost like I haven't talked to people like for 20 years. That's actually not really true, but I mean, but I haven't worked in a corporation, so I haven't, really talked to, in a professional level. Yeah, like usually I've been just staying at home, so it's kind of like a hermit. But anyway, so I started to do this video, and doing this video is great because, on what I mean, in some sense, I mean, on one hand, it that's what I want to do because it give me, first of all, I mean, I like to express my opinions. I have opinions about something. I tell people, and maybe I hope, it's some of the information is useful to guys, and it's fun, to have videos these days. The geeks types, they tends to be like they don't want to do video. Like it's been like for that way for like 30 years. Like in the 1990s, like nobody, okay, in the 1990s, we don't really have videos yet. But anyway, in the 2000s, Facebook began. Facebook is actually the one that began to associate people's real names with their and possibly photo, but beginning with associating people's real names with their whatever they say. Facebook, in fact, we could say Facebook revolutionized the internet that way. At least, that's a good point about Facebook, because before Facebook, nobody ever, especially the programmer types, the geeks, nobody ever uh, actually put real name. That, like, everyone is, and, you go to these talk forums, news groups, everyone is a Batman or a Joker or something. You can still see that. Let me show you. Let's see, Geekhack. This is typical Geekhack. Actually, the easiest way to find a Geekhack link is in my keyboard website, because I know where to look. So, well, actually, I don't know where to look. Actually, go to my keyboard blog, keyboard, and search for Geekhack. That directory, yes. So, okay, I got a bunch of articles. So this one, look at the browser. And oh, this is a great keyboard. This keyboard is from Japan. It's one of the best. And someone has compared this keyboard with uh, truly ergonomic keyboard, which I have, and also compared it with hands-on review. So compared with ErgoDocs. So between ErgoDocs, S-Real, and truly ergonomic, he likes this one the most. However, this one is very expensive. It's like $500, something like that. So it's the Kinesis is just 320. So it's kind of a bit too expensive. So yeah, let's go to Geekhack. I mean that's why we are here. So okay, this Geekhack link. Let's copy it. Let's go to Brave browser Geekhack. Now Geekhack is a website where all the keyboard geeks gather. I mean they are extreme geeks. They are extreme fans about keyboards. They a lot of them they dig into the electronics, the keycaps, the component of the keycaps, the technology to create the labels on the key, and the plastic, the material, the chemistry, and the electronics and switches. I mean everything. They talk about everything about keyboard. Many of them are very deep. Like um, so anyway, so this is a Geekhack. So it's a website for keyboard enthusiasts, and you can see all these people. This guy is Angelic Sedition. Actually, I know that guy. That guy is on Emacs user. He's on Reddit as well. He posts often. Uh, Location Flatland. Flatland is a very famous math book. Uh, we talked about last time. Many of you guys know, mention it. So and this guy is CPT badass. Okay, and this guy is Scotty SC0TTY, and this guy is tip for tissue. Yeah, so internet before Facebook is like this. Okay, you got this bunch of Batmans. Nobody, they don't like to associate real names. Like whenever that topic comes up, all the opinion is about security, privacy. Yeah, privacy, privacy reasons. Um, and Jacobulus. This guy is also very popular. I mean, he's also a nerd. He wrote an article about how ergodox damaged his thumbs. I think it's him. I might be confused with another guy. Oh, or maybe he's the other guy who collects keyboards, like hundreds of them. He collects, really, literally hundreds of the esoteric keyboards. So anyway, you got this Batman. They don't like to associate names, and they all talk about privacy. And but look at today, the privacy is like 10 times worse than in the 2000s. Because partly because these geek people, because on one hand they okay concerned about privacy, but look at their mindset and their actions and where society went. What we got today, we got Google, Facebook, they Twitter, this is all fake news every day. And if you are using a phone, I mean in modern society you cannot not use a phone. I don't have a phone number myself. I actually just got a phone for the first time like 2 years ago when I need to visit a professor. But anyway, so everyone needs to have a phone. I mean, especially Apple just came out today with some kind of electronic payment. So if I don't have a phone, what do I do? You cannot live in the society, right? So, but once you have a phone, the phone, I looked. I got a phone like 2 years ago, so I looked, a little bit on a phone. there's no privacy absolutely whatsoever compared to a laptop. If you have a laptop, doesn't matter it's a Linux, Mac OS, or Windows, you can, for example, in browser, you can turn off JavaScript. You can run programs, Wireshark to see the traffic, who is sending what traffic, even when you are not connected to anything. You can look at all the directories. You can monitor things. So you have control on the phone. Everything is an app. They like yeah, it's a long story. And there's no way to turn off JavaScript or whatever. And so it's 10 times worse, and each company says, and the options are all confusing. There's basically no way. You got a phone, your life is is an open book, known by Google, by Apple, and you have to record your voice, like Siri, what's today's weather, and all that. They know your photos. This thing about the photos. When you get a phone, phone has a camera. Like when I first got a camera, it's like year 2000. Digital camera, they become cheaper and cheaper every year. So today is like basically everyone, at least almost everyone in the world except the very poor countries, has a camera in your pocket. What do you do with the camera when a person, average person has a camera? The first thing you do is to take a photo of yourself. So that's what selfies. Okay, I got some messages. Derivative. What? So what are you saying, Sebastian? It's knowledge. Most relationships are superficial. Please help. Okay, I think we got a troll here. Uh, so privacy is only a problem when you start to get punished for being different. Yeah, I guess. So anyway, so yeah, so let's go back, to the previous topic. So I was saying Facebook was the first. It's an evil company, but at least one thing they did to the internet is that um, it creates, it began the phenomenon where people start to associate their real names to what they say, which is actually most people want. I mean, before that, the concept of internet is like, oh, it's dangerous and it's dark, spread by all the programmer, hacker types. So anyway, back to the so I was talking about Facebook, and I was talking about names, and what's the previous topic? How did we get there? Um, yeah, tech, Donald Knuth, and so shit bass Hankar. Who is this guy? So anyway, back to Donald Knuth, the art of programming, and yeah, why tech sucks. So let's talk about that. Okay, so let's see what. So we're gonna talk about that. Yeah. Okay. Yeah. Well. Yeah. Okay. So tech pestilence. So tech was created because and it's free. And it began with the math communities, and then it spread to programmers. And It's very bad. Okay, the tech is very bad. Yeah, I'm kind of, I actually, uh, Knuth, Donald Knuth. I actually never liked anything, almost anything he wrote. I read lots of his books back in the 1990s. I started to read the art of computer programming in 1992. I didn't understand it. And you know, t- well, partly because, well, that series of books, the art of programming, is actually focused on. I mean, the way he teaches is that he wants to teach you assembly first, assembly code. Assembly code is the heart of actual programming hardware. You have machine language. Machine language, because when you write a program, it doesn't matter what language today, Python, Java, C, the compiler converted to the machine code, and machine code is just a bunch of one and zeros. I mean, the source code of machine code is just 1 0 1 0 1 1. It's just a sequence of the one and zero. That's the lowest level of kind of the programming language. Above that is assembly language. Assembly language looks like okay. Well, I'm getting into that topic, but anyway, so assembly language. So why am I talking about that? Yeah. Anyway, going back. So the art of programming. So that book, I mean, the way he wants to teach that is that he want to talk about. He want to give you a concrete machine to work with. So, for example, if he's teaching you about sorting, algorithms for sorting, there are many ways to sort, a bunch of numbers or whatever. I abstractly, it's a mathematical idea. We understand what it means. So you have a bunch of things, and they have a specific order. In math, there's a thing about order theory. I mean, that's actually the real math about it. Let's see, order theory. Um, yeah, you can read about that order theory, and let's magnify. So order theory is a branch of math which investigates the intuitive notion of order using binary relations. Yeah. So it's a bunch of things. Then it relates to yeah, math is amazing. It relates, yeah, poset. If when you study a category theory, you also get into poset. Partially ordered sets, yeah, those are all critical information. Then you'll get into lattice theory. So anyway, and orders, that's a mathematical theory about orders. Lattices, yeah, bounded posets, lattices, complete lattices, directed complete partial order, and stuff. This is great thing, I really love this kind of thing. Math is my true love, but she's been difficult. And so programming, so you want to order, you want to sorting algorithms. So you can talk about it in a mathematical sense, you order. But if you want to talk about programming, well, you can discuss various methods for sorting. On Wikipedia, there's a huge article about sorting different methods. So you can talk about it. You can teach the algorithms about sorting. Like for example, bubble sort. You just compare two numbers. Which one is greater, then you swap them. You swap their order. So this is an abstract way to teach about one specific sorting algorithms. But Knuth, his idea is that he doesn't like that. He wants you to actually work with a machine, because in his opinion, in a preface or somewhere I read that to actually really understand sorting or anything about programming computing, you have to understand the machine, the something you are working with, not the math elements, not the math elements, but actual uh, assembly language. Yeah, it's called a machine. It's just called a machine. But different CPUs, different. Yeah, let's go into that topic. Since this is talk show, so let's go random. Then we go back to talk about the tech pestilence. That's a lot there too, because that that one is an hour by itself because it relates to formal languages. It relates to yes, formal languages, and formal languages relates to the heart of computer science. I mean, the theoretical computer science, the most difficult problems in computer science. And it relates to proof theories, proof systems, which is we are trying to invent today, like IDRIS programming language, COQ programming language. Those are proof systems. They are intimately tied to math notations. Um, so these subjects are all like related, all related. The meaning of notations, the semantics of notations, how it relates to mathematics, and the social consequences of a notation, and the notational systems. What are they? The history of notations, and computer systems for notations, and math algebra systems like Mathematica and Maple and others. They are kind of all related. But anyway, so let's talk about that. I was saying about the machine, CPU, and compilers. Okay, maybe a little bit. Yeah. Let me try to manage the topics, and let me try to be coherent. So hold on a second, my roommates. Hold on. 要去啊，我不去了，我1小时，我有9:40，讲话。下次再去。So notations. So we back to the machine language. Yeah, let's talk about. So let's go to uh, semantic noodle. Let's go there. Hey Danielle, let's do. Okay, so notations. So what I don't know about C. Most. I'm into math, so my background is mostly math. So my perception about programming language is mostly math oriented. And I like it that way. And I don't actually know much about low level languages such as C, or it's 3:30. Okay, low level languages C, or I never coded assembly languages, and I don't know about the CPU architecture, the memory stuff. Those are, I don't know nothing about it. Systems programming, that field, I know very little. Or even how to write compilers. I don't know nothing about it, but I'm trying to learn. But in the past few years, I started to read about them, and they are quite interesting. Especially the CPU design. I mean, the CPU design that powers all our computers today. The Intel CPU chips, whatever chips, Sparks chips. They The design of the CPU is a huge topic. I mean, I realized, okay, that's, and it's non-trivial. It's not, and it involves several things. It's extremely mathematical, okay, for one aspect, and also it's engineering. The physical engineering of making the chips, the design, what is possible. Even if you have a mathematical model, sometimes you cannot build chips. And also there's a practical aspect and efficiency aspect. You cannot just design an ideal design of a CPU and say let's make it. There's lots of constraints, cost, and efficiency of computation. It's not just about elegance or whatever you want. So there's so many engineering constraints, and but even from a pure mathematical point of view, that's also very interesting. So I wrote something about that. Daniel, hey, informatic. Uh, so let's see. I got. Yeah, I sometimes I have a hard time to find where is my articles. So on the rectification of programming language spec by formal language ontology. Okay. Uh, math versus programming. What versus how to? A class of computer languages, math languages. Yeah, that's a great article. Brain fog. Yeah, I one time I did a homework for someone. He paid me to do a homework, and that's a brain fog. Brain fog is one of the language that programmers, the hacker types, like to cite all the time because and actually when you do brain fog, it's very you start to get into the low level programming and you learn a lot of things. I learned a lot of things because in high level programming like Python, Ruby, JavaScript, or Lisp, if you live in this level, you never get exposed to some, what's actually going on, in the lower level. And some of your concepts about programming languages or programming or computation is actually just wrong. Yes, because yeah, you have to have like exposed to the level. For example, before, you might think there's, for example, Python as opposed to Perl. Python people like to say, we try to make things so that there's only one way to write it. You know, an algorithm or whatever. Like there's just one way. While on the other hand, Perl is fond of, there are more than one way to do it. That's their slogan, because uh, but actually, if you look at, if you code low level assembly, such as BrainFuck, that's a very low level language. You realize that there's no, it's impossible to have one way to do it. There are like a million ways, for one specific algorithm that solves one specific goal, such as sorting, when we talk about sorting algorithms, we are, for example, you go to Wikipedia. There's lots of articles, and but they are all talking at the high level. Like you just swap two numbers and that's it. But at the CPU, when you have to like electronics is going around in your machine, the billions, mega billion, giga billions of electronics. They are doing their stuff. Uh, and for example, for example, I display a characters, unsorted here. What is u, what is n in a CPU? So u is a byte, just eight digits of one and zeros. And so so it's very complex. I mean, it's very complex. So I mean, so anyway, okay. So at the low level, when you want to you kind of get to see that it is impossible. It's basically impossible to have like one algorithm that is supposed to be the best. Okay, uh, because there are a million ways to do it. And like if you look at into brain fog, you'll see it. But anyway, let's get back to the um. Okay, let me just try to find the article quickly, and let's get back to. Okay, cost of computer language operations, uh, programming languages, and this and its machine. Okay, this is very interesting topic. Um, so programming languages and its machine. So I'm interested in programming languages. I think which is better. Haskell, Golang, or why it's better and that way, this or way, or functional programming, or OP. But then you have then I start to look into the CPU design, and I learned a lot of things. So okay, so yeah, that's what I want to try to find. Instruction set architecture. Now, what does that mean? That is basically a mathematical abstract mathematical idea that captures a design of a CPU. So it's called instruction set architecture. So what does it mean? It's just an instruction set. Basically, you have a set of things. Each thing is an instruction. What does the instruction mean? Instruction means like put this number in this address, or uh, uh, um, yeah. Let me read it. It's probably best there. So a machine. So instruction set architecture. a machine can be abstracted into instruction set architecture. For example, a set of instructions. Yeah, I mean, that is a set of instructions. This makes up a machine language. Okay, that's the key, the machine language, the lowest form of programming language. Each instruction do things like move this stone over there or put this number here, add two numbers together, and things like that. So each instruction, instruction, they just do one very simple things, add these two numbers. So in a CPU, you have like registers. A register is like storing a number, which is just a sequence of zeros and ones. You have one, two, three. Let's say you have 32 registers, and instruction comes. Instruction tells you take the number register from register 1 and take the number from register 2 and add them together and put it in register 5, for example. That's one instruction. Another instruction might be, let's say, remove empty register number 4, something like that. So so you got a bunch of instructions, and you have the instruction set architecture. Okay, once you have that, you are given once you have a designed one specific instruction set architecture, then you'll have microarchitecture, which is, when you actually implement the ISA, instruction set architecture, ISA. When you want to implement a specific ISA, by implement I mean, you actually have to design the chip that, when an instruction comes, certain electronics, electricity flow happens, and that adds two registers, for example. You have to, that's, electrical engineering. You have to get, it's the electricity that's doing the work. So you have to design that chip. That thing is the chip you have to, when you implement a ISA. So ISA is like a abstract mathematical thing, but you need to implement it. That means design the chip, the electronic flowing around, and that is called microarchitecture. I mean, because there are so many ways to design the chip that, that does the instruction stuff. So you got the microarchitecture. Um, okay, so that's the two things I want to say. Back to the Knuth, So when he teaches algorithms, let's say sorting, he wants you to have a instruction set architecture. So he just simply just saying, okay, just swap these two numbers, compare them, which one is larger, then swap them. Instead of saying that, he wants you to actually get down to the instruction set architecture. So it's like you have to call an instruction that, maybe there's an instruction that swap to register the numbers in two registers. He wants you to deal with that. But because, in practice, every different machines have different CPUs, so they have different instruction set architecture. They have different microarchitecture, and they change every year. Intel has, Pentium, then and what are the others? Yeah, all these are different chips. Xeon, Spark, MIPS. So they change it all the time. So what Knuth did is that he created a abstract instruction set architecture, which is called MMX, I think. So let's look at the art of programming. So how is everyone doing? So far so good. Let me know where I'm going. If I'm uh, not. So yeah, so this is his book. It's still going. I don't think he's gonna finish it. He's very old. You know. Hey. So he's very old. I actually met him when a friend, a female friend, interesting. She contacted me, say, hey, she says, hey, you want to go down to the computer museum, which is just down the street, over here in Mountain View where I live. So one day I went there, and Donald uh, Knuth, he's there. Knuth he's there, so I saw him. He's very old, he's like 70 something, and you can see you can see his videos in the last couple of years on YouTube. When you are very old, it happens to everyone. You cannot 81. He's 81 years old. You cannot talk. I mean, you cannot even talk well. Not even mentioning your coherence or whatever. You don't even talk well. So anyway, so let's go back to let's search for MX. Uh, okay, volume 1 fundamental algorithms, volume 2 semi numerical algorithms, sorting and searching and stuff. He wrote an entire volume on sorting and searching, volume 3. That book is like this thick. um, Syntactic algorithms, compiler techniques. Yeah, it's planned. Volume 5. Compiler is the critical importance. Oh, and theory of context-free languages. They are of critical. I mean, wait. Hold on. Okay, volume 5, combinatorial algorithms. So volume 1, 2, 3, they are very basic. I mean, yeah, they are algorithms. They are important. And numerical, yeah, they are I mean, they are essential. But then, I mean, all these are kind of like all very essential. I mean, the heart of the programming computer science. Because you see, volume 5, then you have theory of context-free languages, and volume 7 or volume 6, volume 6. Wait, shit. Volume. Okay, volume 4. Let me turn off autoclick. Volume 4 is combinatorial algorithms. Volume 5 is syntactic algorithms. Volume 6, the theory of context-free languages. Volume 7 is compiler techniques. Now let's look at volume 7. If you don't have a compiler, nothing happens. We are back to the 1960s. You have the compiler to actually start to do anything basic. You need a C compiler and so on. You cannot just code in machine. I mean, you cannot. It's impossible to code in machine languages. So you need a compiler. And before you have a compiler, you need to know about the context-free languages, which is a grammar specification of a language, so that a program that can actually read your code and understand what it means, then translate it to the machine language. So in order to have a compiler, you have to have a theory of context-free languages, which is the topics I love. That it has to do with formal languages, parsing, regular expressions. Regular expression is a mathematical theory originated from there. But today, when we talk about regular expression, it has nothing to do with that. It evolves and becomes to us, most programmers, regular expression is just a practical tool, for pattern matching strings. But originally, it is also pattern matching strings, but it's used in a theoretical context to solve or express certain languages grammar, or to help. But anyway, so you can see that many of his works is just not done. It's not likely gonna be done. So 1, 2, 3, 4, he got these 4 volumes. So okay, back to the my previous topic. So I was saying, when he wrote the book, he created the MX. Why can't I find it? Okay, let's search for uh, Donald Knuth MMX. That way you'll find it. MMIX. Okay, so that's why that I cannot search for it. Close, switch, search MMIX. There it is. So he's got a machine. Remember we were talking about machine CPU design, ISP. ISA, the instruction set architecture. Then you have microarchitecture, which is the actual implementation of the ISA as a chip, a hardware. That's microarchitecture. So Donald Knuth created the MMIX. Okay, let's read it. MMIX is a 64-bit reduced instruction set computing. Okay, so designed by Donald Knuth. Okay, so what that means is that MMIX is a instruction set architecture, a specific type called reduced instruction set. Okay, but anyway, it's just an instruction set. It's a mathematical abstract. It's a abstract idea. It's a set of instructions. So once you have a instruction set, uh, you know, you basically have a machine. Even you didn't build it, even you don't have a microarchitecture, even you don't actually build, a physical thing or chip, you know, but you got the instruction set architecture, which is actually precisely define a machine, because you have a bunch of instructions and each instruction is exactly, what they do. So uh, Knuth created this MMIX instruction set. So the purpose of this is so that so he can use it in his book, The Art of Computer Programming, to teach algorithms. So when he's teaching, for example, sorting algorithms, he doesn't want to just say, okay, bubble sort is just, swapping neighboring, elements until something happens. That doesn't work for him. He has to get down into a instruction set, um, so yeah, that I think that kind of wraps up what I originally was going to say. Let's go back to tech pestance. So I think how long have I been going? 40, 50 minutes. Okay. Okay, MMIX. Thank you, Norman. Um, so interesting talk. Thank you. Did you like the Computer History Museum? No, not really. I mean, it's kind of silly to say because I went to museums a lot in my life because that's my thing. I like those kind of things. Science museums, laser shows, planetariums. And also almost all these museums usually they have a lot of kids go there. Children. They have like toys. Math toys demos. But usually it turns out usually I didn't find them interesting, all these museums, because basically once you went to a few, everyone looks the same. You have a bunch of, I mean, and the things they cover is very like popular. They have to cover things like everyone, like non-scientists uh, appeal to the non-scientists. So children or you go there, they and laser shows. But for a nerd, or for a programmer, for example, we are programmers, or most of you are, you go there, you don't, uh, you know, yeah, I didn't find that, these museums, too interesting. It's kind of boring, actually. But anyway, you do get to see old machines. They build the not ENIAC, but the famous calculator by Babbage. Oh, Babbage. What's the name of the machine? Which is a kind of like the first computer, but with gears. Difference engine. Okay, you guys heard of that, right? Di- uh, uh, ENC, difference engine. Yes. There's a lag like between whatever you typed until I see it on my screen. I think there's a 5 second lag. Yeah, difference engine. No, no one is on fire. Okay, so I went there, so I saw this machine, but I didn't see them actually run it. Then I also saw one of the earlier computers, like they have 60s computers where you have vector based screen that shows, like you shoot a game, But anyway, that's a computer history museum, which is down here in Mountain View. You can just search that word if you're not here, and you'll find it. There's their website and also Wikipedia article. I think on Wednesday or something it's free. Um, Oh, Babbage designed the second one. Yeah, Babbage also is a interesting character. He is a sad fellow. He has great ambitions, and he designed all these things, and but he never completed anything, and he died a very like a bitter man. Like Stephen Wolfram, he did the research. He wrote an article on Babbage one time. I think it's him. I think he did, or maybe someone else. But anyway, it's like you cannot find yeah, analytical engine, right? So and you cannot find a photo of Babbage that's smiling. He's bitter. And complaining about all things. He never finished his machine. Uh, yeah. So computer museum, computer history museum. And these museums, they are, again, I suppose, non-profit, and they want your money, and well, yeah, it's good. I suppose it's nothing bad about it. Okay, so yeah, Donald Knuth. So he created MMIX. So yeah, I was looking into. So I learned this just about last year. I looked into, and so this ISA instruction set architecture is uh, was tremendously interesting because you have to all the computing happens. You have to have the chip, and also once I you know read a lot about this, once I studied this subject, I learned a lot of things because so many things that just in the past 20 years you hear it all the day or every day. Oh, Intel created new chip. Oh, Intel has Xeon. Or risk chip. RISC chips. Or x86 architecture. Like when you download Emacs, sometimes they'll ask you, download x86 something something. So what does it mean? What do you mean x86? Or all these names, you start to understand. uh, I start to understand. You might have, well, I mean, if you are a C programmer, okay, if you are a system programmer or Linux, you are interested a lot. A lot of programmers are interested in that, especially the hacker types. They are interested in low level stuff. Assembly, computer. So then you already know this stuff. I'm kind of ignorant, but anyway, so I learned about this last year, and it just it's fantastic. um, and so all these years, I've been thinking about programming language design. That's all. I'm from a math background, so it's all high level. But at the bottom, these things also requires tremendous design, and not just abstract design, because you have to actually create the chip to so that your design must satisfy many constraints, cost constraints, and so on. And also, it must be very fast because it's highly competitive. Um, yeah, so there's a lot of things, not non-trivial things. I mean, uh, besides the social parts aspects, that's interesting, but those also, many of these are deep mathematical questions. For example, there's SAT. There's a problem about SAT, which is in formal languages a kind of an open problem. It's a SAT. Uh, not the exam SAT, but uh, okay. Let's go to disambiguation. Okay, language and linguistics, government, language, organization, science, math. Okay, here Boolean satisfiability problem, which is one of the um major chapter of theoretical computer science. So it says in computer science, the Boolean satisfiability problem is the problem of determining if there exists an interpretation that satisfies a given Boolean formula. That's a bad wording, but because if you read it, you don't understand what it means. That's not okay. In other words, it asks whether the variables of a given Boolean formula can be consistently replaced by the values true or false in such a way that the formula evaluates to true. Yeah, that's a good way to put it. So basically, you got a collection of uh, uh, equations like a and b equals to c, then b or a equals to a. For example, you got a bunch of them. You won't find the values for any of the variable a, b, c, or more variables. You want to replace each variable by either true or by false, such that all of them becomes true. Something like that. Okay, I think you get the idea. So I mean, I'm sure they have examples here. So basically, each one of the equation is a Boolean expression. So you want to replace the variables x1, x2, xn by, yeah. Okay, this is just not a bunch of equations, just one expression, a Boolean, expression. So you want to, is it possible? So is it possible to replace any of the variable by true or false such that this whole expression is true? So this is not um, so the real question is about, so that is the Boolean satisfiability problem. The real question is about whether the question is about how can you find the efficient way to solve this problem. Of course, you can always do brute force, but that doesn't work because I think because this number of variables can be like millions or something. Yeah, but anyway, I don't know about this topic much. So, but this is one of the things I learned when you design CPU. When you design ISA instruction set architecture, you have to. I think this is one of the essential problems. I mean, you have to solve. Uh, okay, so GP2 says, hi GP2. So since you are talking about low-level design for systems and languages, what do you think of Terry Davis and his creation Temple OS? Just curious. He was schizophrenic and died tragically last year. Yeah, someone told me that. So I looked into the guy. So this guy Terry Davis. You can go to YouTube and find his videos. So he's a very extremely weird guy. He's a, yeah, schizophrenic. Schizophrenic is very different from schizoid. Okay, I'm a schizoid, which is a loner personality. Okay, but schizophrenic is someone uh, who has like hallucinations, like you see things that are not there, like you, I mean, you see or hear things that doesn't exist. So I watched some of his videos. He's talking about what was his beef about CIA or FBI? He's like swearing at the FBI or CIA. I forgot which one, but all the time. And yeah, very weird person. But he was, yeah, because he's a schizophrenic, but also because but I mean, he's extremely smart and capable. He created this CIA. Okay, he created this Temple OS, which is a extremely small, what, a few megabytes, like a full OS. I saw it, on YouTube. It actually has a 3D modeler, like CAD, like AutoCAD, a simplified version, like 3D modeler. and, and the editor and the compiler, the whole, it is a operating system, and everything he wrote himself. Yeah, so that's amazing. I don't know nothing about operating systems, but I can see, he's someone out there. And he looks like he died last year. Supposedly he ran into a train. It's not certain. It's either suicide or just by mistake. Maybe he's drunk. We don't know, but yeah. So that guy. So anyway, let's get back to the. Okay, let's talk about this original topic. Let's talk about that a little bit. I'm still learning about doing videos, of course. Yeah, I was mentioning that because it's been like half a year, almost half a year now. I've been doing videos. I started to do it every day since maybe a month ago. But I'm learning things. So I'm learning, talking and giving a presentation, and for example, right now I'm getting more better at you know like like I wasn't sure, something like this Kazaa talk shows, currently I wasn't sure. Sometimes I want to teach actually teach something, one narrow specific item. Sometimes people like that, especially Emacs, because a lot of people following me because of my Emacs stuff. But on the other hand, I'm not sure, because I mean, when you teach a specific subject, sometimes it gets boring. But when you are like doing a talk show, so-called talk show, I mean, there are lots of talk shows, radio talk shows on the internet. They get popular because people want to see you just talk about things, not as opposed to, for example, if you are a professor or you teach math subject, for example, there are a lot you don't get. It's kind of boring. But anyway, let's talk about this tech pestilence. So yeah, I don't like tech very much, and it's one of the things, it's embraced by all the elite hacker types of programmers. Like any opportunity, they'll tell you like, you should use tech and stuff. And tech, and I was very disappointed by Donald Knuth, because he created this thing. Yeah. So before I was mentioning, I read quite a few of his books, his font books. I tried to read the computer art of programming, and his other books. He has collected essays and others. I didn't like his stuff. I mean, there are other, computer scientists I do like, but it turns out not much of his style and his stuff. He's kind of the nerd. He's the typical, the nerd qualifies him in the sense that I'm also a nerd, but he's the nerd, like he's the squarish, not funny kind of guy. you know, and so I don't like his jokes. So anyway, so he created this tech. He also created so-called, what literate programming. Yeah, I fucking despise. Oh, I don't despise it, but it's stupid. It's silly. All the hacker types. They want to like. I want a literate programming. It's very popular in the Emacs org community, and back then when Perl was all over the world, it's very popular in the Perl programming community too. And usually these hacker types, they don't actually know what they are doing. Literate programming is something specific. And it's very silly because literate programming, okay, the heart of literate programming is that you are a programmer. You actually write for other humans to understand. You don't write to the machine. Writing the algorithm, I mean, for the machine to understand is only a part of it. It's like the second purpose, like the side effect of your literate programming. You are actually writing an essay describing the algorithm to other programmers. In other words, that is documentation. Okay, so this relates to documentation heavily. That's the heart of literal programming. You write essays communicating your algorithms to other human animals, okay, or human beings. Um, but so a lot, hacker types. Oh yeah, we want to, I like literal programming, org, mod, they and Perl people back then. You don't hear them anymore because this hacker fad, they kind of die away. Then you have the next new one, next 5 years. You don't know history. You don't know. Oh, they are this, Perl people. They are so much into it. But anyway, so literate programming is about writing essays for other humans to understand. Uh, but look at, you notice all these people who are a big, who talk about literate programming all the time in Emacs community or in Perl. They don't like write documentations. You look at their stuff, they don't know how to write documentations. They are not concerned about technical writing. They are not concerned, they have never thought about, actually take the time to study technical writing or documentation. It's like they don't care about that. So the reason they follow, they seems to be a fan of literal programming is purely of the like elite hacker, the fad aspect. Because this is Knuth created literal programming, therefore we're gonna do literal programming. Oh yeah, I'm excited about the terminology of what they have. Like they have terminology about like compiling. I'm not. I forgot the terms. Um, so let me read some comments. So, anyone remember what's the terms for the literal programming? Like you have to spit out code, like compiling or merge code, something like that. So Norman says, if you need to write text extensions, the language is horrible, and as a user, you need a lot of time making small random changes to influence the layout system indirectly. Yeah, exactly. GP2 says, I could never really get into tech. I'm not sure people praise and swear by it like crazy. It seems really different and too much effort for simple tasks. Exactly. I mean, I agree with both of these points. And okay, so there was literal programming, but back to the tech. So I don't like tech because okay, let me just maybe take 5 minutes. We can finish this 5 or 10 minutes. So tech, so this article, you can let's see, let's turn on JavaScript. Okay, it's already allowed. So let me show you an example. Okay, so suppose you want to write this. Okay, tech, the granddaddy of syntax soup. Yeah, worse than C Sprint. The language C created Sprint off, Sprint F. Okay, I hated that because that's a like a little language. Like yesterday we talked about. The C, in my opinion, C and Unix created everything that's wrong in the in computer industry. So C has this Sprint F. You have like you have a string, then you have little percentage sign to do things. Okay, Basically, you C, and C++ and Python, they like all these special syntax sprinkled throughout your language. Like if you want to do this thing, you have a special syntax over here. If you want to do that, you have a special syntax like over there. You have to learn each one of them, individually, and they are ad hoc. Like there's no coherency. Like like there's no simple a few principles that governs everything. No, it's like just why do I mean everything is just ad hoc. But anyway, TeX is even worse. TeX. So suppose you want to create these math expressions. So and this is what it looks like in TeX. Okay, this is what it looks like. It's a crap. It's a syntax soup. It's hard to type and there's no structure. Now remember, there's no structure. Okay, all structure. When you look at math expressions, look at this. There is a structure. What do you mean? For example, let's look at the first one. First of all, this sign greater than sign. Okay, that's a specific greater than sign. That sign, you can think of it as a function. It's a binary function. This sign is it has a uh, hierarchy on the tree than these two. So this one connects these two. Okay, and well, this one actually connect the left and right, and this one, the equal sign, connects the left and right over here and here. Okay, and for example, if we take this part, we can further dissect. So this part, the sum symbol is at the top, then the k and n equals 1 and the 1 over n is its arguments basically. So this greater than equals sign, the left and right is its arguments. So you can think of it as functions. It has a structure. It has a tree structure. Similarly for these, equal sign has two arguments, the left and right. The left part we already covered, but let's look at the fraction. Let's look at this fraction, 1 over 3. So fraction is a function. It has two arguments, 1 and 3. Okay, so and plus sign is also a so anyway, it has a tree structure. You might know, abstract syntax tree. It can be converted to abstract syntax tree. It has a structure. Okay, um, any of these. Okay. So if you use TeX, to do it, it looks like this. Basically, all structure is lost. Given any TeX expression, you cannot recover the original structure of these expression. You cannot recover it. Now let's look at the alternative. Here's a Mathematica syntax. Now you can see. Okay, let's look at this one. Let's magnify. Okay, look at this one. So you have this. Okay, so it says sum, then bracket 1 over x. Okay, sum has two arguments. One is 1 over x. The other one is a list of n, 1, and k. Okay, now if you look back, okay, so let's look at back the. Okay, I cannot show both of them at the same time, but look at this expression, this one, the first one, and look at the Mathematica. You can see the Mathematica expression is clear and logical, and also in a simple grammatical way that as a programming language you can actually parse it easily. Okay, so here are other Mathematica Wolfram language syntax. Okay, to represent these math expressions. In fact, if you type this in Mathematica, you can press a button and they will be rendered like these. Okay. Math notations. So the first thing about TeX is that it has no let me show you the Mathematica so this is Mathematica. Okay, you can see it's rendered. When you type, you press a button, it's rendered into two-dimensional uh, rendering, like this. But what tech does, first of all, it doesn't have structure, and it basically, what the text approach is that they are like for type setting, so-called type setting. They create little bitmap graphics about, okay, which number to put where, maybe a 1 pixel up a little bit, or maybe a little bit to the right 2 pixels. You you write these expressions to adjust that, like 1 little pixels up here. That's what tech is, the heart of tech. It's extremely bad. Why the hackers types cite it all the time? Because first of all, the most fundamental reason is because it's free. Everyone loves free things. When you have something free, as long as it's reasonable, it does something. It wipes out any competitors, anything that you have to pay. It's like a virus. It wipes out everything, like Unix and Linux. Okay, you may not agree, but I talked about that. It's when you have a free, you wipe out everything. Um, that's one reason. That's the most important reason. The second reason is that uh, oh yeah, so the second reason the elite hacker types love to cite about tech or like it every day is because Donald Knuth, he's famous, he's a celebrity. So in a sense, it's like all the young girls, they follow Kardashian, Kardashian, who became famous because she made a sex tape, and she is now like a billionaire, like you know so you have like millions, 10 millions, 100 millions following girls following her. On her Twitter, she posts, women things like, "Oh, this bikini is $4,000," and all the girls, going to buy it. Uh, it's like that. So in programming, you have something similar. My eyes gets dry. So in programming, it's like same kind of phenomenon. Donald Knuth created this, so all the programmers go crazy. Not all. The hacker types, those types who think they are also hackers. They want to follow the hacker's path. Those kind of people. So yeah, so that's basically why I don't like tech. Okay, the structure in math expressions, I talk about that. You can see this simple expression is a tree. The problem of tech. Okay. Okay. So what is alternative? Actually, I don't really have a good answer. Uh, for one thing, the one good alternative is Mathematica, but it's proprietary and you have to pay. So a hobbyist version is like $200 or something. So that's one way to go. I mean, so you have to pay and you go to Wolfram Research, you buy Mathematica. Then everything is it's wonderful. I mean, you just type these, you can do math, complicated math, you can program, um, yeah, but it's a commitment. Once you buy Mathematica, well, I mean, if you are a programmer, working in a company, that's not too much money for a hobbyist version, and but I mean, you pay, you do have to pay, and once you pay something, you know, you might do something with it. I mean, it's a commitment. If you want to code Mathematica, you actually have to spend time to learn it, to study it, to program in it, or write page, maybe, okay, maybe you actually have a need to, publish math notebooks all the time, write these. Then it's a good choice, Mathematica, which I do recommend. I programmed Mathematica for 10 years every day. I'm heavily into it. I know it inside out. In the 1990s, it's got a book this thick, 1,000 over 1,000 pages. Let me show you. I read it from cover to cover 3 times in different years in the 1990s. Um, Fourth edition is the last printed edition here. So yeah, it looks like that. This is a fourth edition. This one is printed around 1999, something like that. Oh, fifth edition. But anyway, they stopped printing just like every other companies around in the early 2000s. But anyway, this book is like this book is heavy. It's like this thick. Yeah, this thick. Um, okay, so yeah, I programmed a lot Mathematica, but I haven't done so for 10 years at least. Um, so yeah, what is alternative? So you buy Mathematica, that's one alternative. There are some other okay, let me talk about the other thing. Okay, MathML. Now MathML is a alternative. It's a XML based technology for the web, so you can display math formulas on the web. But Google killed it in their browser like 3 years ago. It's very sad. Google becomes so evil, and partly because nobody, all the geeks wants to use these. We love these, but in reality, if you look at the real world, nobody. I mean, who is doing mathematics? People want YouTube, videos, not math. There's no so you know so Google is not gonna get much out of it. They killed it in their Chrome browser. Um, but anyway, MathML is very verbose. When MathML was beginning to be created, I was at Wolfram Research, 1995. So Wolfram Research sent representatives to the W3C, committee or whatever to to help or participate in the creation of MathML. But anyway, it's pretty bad. I mean, you got it's extremely verbose. I mean, look at this formula. If you want to type this, it's like 100 lines of MathML. It's this one. X equals. Let me see. Yeah, this one. Basically unreadable. Um, but anyway, MathML is one option. It's not really supported in Google Chrome, but I think it's still supported in Firefox. But because of the situation, you could say it's not really. I think Wikipedia also supported. You have to go to Wikipedia and log in and turn on, go to preferences and turn on use log in and say there's a preference. You have to say use mathml. The otherwise you'll just use a image like this one. This one is an image. The problem with image is that you cannot copy. The advantage of mathml is that when you see a formula like that on the web, if it's using mathml, you can just select it and you get you get a sensible copy, either mathml itself or something sensible, something like this. Okay, then you can paste it in some programming language. I mean, the ideal of mathml is that it's allowed copy and pasting. For example, you see a formula, you just copy it, you go to Emacs or whatever application, you just paste it, and it becomes a valid program, and you can press enter and it'll run. You can just put the value to BC, AC, and it'll just run. So that is the advantage. That is the reason. That is part of the reason. Okay, why this is extremely superior than the tech fuck. The tech. When you have tech, you got this. There's nothing you can do. It's very insulting. Is that it's not computable. The tech, and LaTeX is for typesetting. All it does is just generate pretty pictures. It generates bitmaps, or vector graphic. Anyway, it just generates pictures. This you copy is not computable. These things are computable, and you can substitute, Kate a number and it come out a number. We are talking about programming languages here. It's supposed to be, you know, Donald Knuth, one of the premier, the top computer scientists should know this. You know, you created this thing. It's not computable. It's just for pretty printing things. What the fuck? And also the way you create the language, the way it's structured, you have no structure, so it's pure garbage. So yeah, so that it's great. So there are two things: you lose structures, and it's not computable. I mean, it's not it's not actual. You destroyed everything about math. This all essentially almost all math expressions, even the abstract algebra like category theory with arrows. You see category theory diagram, they have arrows, they have structures. They can they have structures. So essentially all math um, formulas, you open any physics book or whatever, however complicated, they have structures. And they anyway, so tech, you lose structures, and you are not computable. And Knuth created, he just went into the wrong path. you know you cannot blame, I mean I cannot blame him, because it's not like, I mean, because I'm looking at this from a hindsight. you know from this point of view, you can see, oh, they should have, maybe why didn't they design it that way in the beginning. But things, that's from hindsight. When he designed it back in 1970s or 1960s, late, I think 1970s. He just wanted to create a digital typesetting system. That's for typesetting, because back then there's not even digital typesetting yet. We don't have desktop publishing, which Apple kind of brought, created in the 1990s. So he just want a computable typesetting system to help him print his the art of programming book. That's the origin of tech. He want to, he write this book, and he want beautiful fonts and stuff. And there's, you know, difficulties. So that's why he created tech to do that. But from today's point of view, or even from 1990s, you can see it's really bad in many ways. It's a wrong direction. It's just not the right direction of how you want to go. So Mathematica is the alternative. Math ML is the alternative. Of course, if you use Mathematica, it can export to TeX or MathML or images. Then okay, I think that's about it. I think let's see questions. Yeah, Norman says, amusingly, you can export LaTeX from Mathematica. Well, because Mathematica is you know a company, they want to make money. When people use Mathematica, they want the feature. Otherwise, why am I buying this for? Because as a matter of fact, the scientific community, many of them accept, they require TeX and LaTeX. So Mathematica is a tool. You has that feature, so you get your money worth. You can buy Mathematica, and you can export to LaTeX or others, but you cannot use. So break the loop says, okay, let me go to the top. Uh, okay, break the loop says you cannot use Mathematica to write and print math notes. So what is the alternative? What do you mean you cannot? You can. I mean, well, you can use Mathematica and to write and print math notes. You can print it out. I mean, you start a Mathematica notebook just like today's Jupyter. Today there's a Jupyter notebook, very popular in Python communities. You can just type it in it, and print out. You'll print out with formulas, or the math formulas. Unless you mean something else. Okay, so then Daniel says expensive proprietary system. Mathematica's built-in graphics tool are fantastic for exploratory visualization. Yes, it has very general purpose graphics. Yes. Okay, Daniel says, but consider Mathematica doesn't have a good Emacs interface of a well-supported Mathematica mod. It well back in 1990s it has many Emacs programmers has written Emacs interface to Mathematica. The way Mathematica works is that it's an application. I mean, you can think of it as a application, or you can think of it as a programming language. Now, for vast majority of people who use Mathematica just for doing math, like they want to find the integral of something, derivative, or solving equations, they are using it just like an app, like a calculator. So there's no actual programming involved. I mean, you just type some equation like solve, then type some equation. You press enter, it'll give you the solution, or differential equations, solutions, and so on, or matrices, or multiplication of matrices, and so on. You use it as a calculator, or you want to plot 3D stuff or surfaces and so on. So most people, scientists, or a lot of people in NASA, for example, they use Mathematica, these scientific organizations. um, so that's one way to use it, but then sometimes you get more advanced, like you solve some equation, but you need to combine these two solutions, and uh, maybe sort them, and then select some part such that they satisfy some other equation or constraints. Then that's your final thing you want, like in engineering, the scientists, or maybe physics. So once you get the next step, besides using it as a calculator, you a little bit programming is involved. But of course, because then you start to view it as a programming language, because then you can get more and more involved, because for example, I wrote many packages in Mathematica to do things, to do visualization and stuff. uh, for example, let's go to hand curve notations. So some math. So I wrote this this is back in 1997, Visual Dictionary of Spatial Plane Curves, 1995 to 97. So you have many of these has animations. Um, let's see. So all these are created in Mathematica back then. So let's look at this is a cauliflower, interesting fractal, and also the shape is a equiangular spiral. Equiangular because from the center you shoot out a line called a ray in any direction. It'll contact the curve. The angle is always constant, like 80 degrees here. That's why it's called equiangular spiral. Of course, the degree can be different. So if the degree are different, you got different shape of curves. It's called equiangular spiral, but also more popularly known as a log spiral. Log spiral. Anyway, so let me show you a animation. So let's see that. So I wrote Mathematica notebook this back in 1995 to create these animations. Today you don't need my package. It's much easier because Mathematica in the past 20 years they have added lots of things, so it's much more easier. To create this just one line. So back then I wrote a package that does this. So the package is like few hundred lines, but you just have a function, then you can just one line of just a function, you can create this animation. But today is kind of like built in. um, So yeah, so that when I'm talking about Mathematica, so you can see it as a programming language. Uh, so yeah, okay, back then, okay, Mathematica, so it's an application, right? But actually, it comes in two parts. So it comes in two components. One is called the kernel, one is called the front end. So the kernel is kind of like the engine that actually does all the computation. The front end is actually what you see, the notebook. You can think of it as a IDE for Mathematica, the default editor, in other words. So the kernel actually do the computation. So whenever in the notebook, when you click Mathematica, it opens a notebook. You type and you press enter. They say solve equation, solve some equation, and it gives you an answer. What actually happens is that when you press enter, the front end, it's called the front end, the notebook. Okay, the front end sends messages to the kernel in a protocol called it used to be called MathLink. I'm not sure what's called today. I think they might have changed the name. The protocol was called MathLink. So anyway, the front end sends out the equation to the kernel. The kernel computes and responds, sends response to the front end. Then the front end display the result. So that's how it works. So it has two parts. Now, obviously, the kernel can be anywhere. It can be on a remote server. It can be, but even on your desktop, it's different. You have a kernel, you have a front end. So you can have 100 person log in to use the kernel. So that's how it works. So people has written Emacs front end to connect to the Mathematica kernel. So you use Emacs, you type something, you press enter, it sends it to the kernel, and the kernel sends reply. Then it shows result in Emacs. So that was one way to use Mathematica back then. But today, uh, you can still find Emacs package for Mathematica, but it's not well developed because most people just use notebook. Because notebook can display graphics, animations, sound. It's hard to do in Emacs. You can kind of, but it's hard. So you don't get much. And the person who writes that, open source, you don't get paid. So it's not very popular. So anyway, that's it for today. For wow, 100 minutes. Any questions? I think that's it for today. So we covered quite a few things about low-level programming, about assembly languages, about instruction architecture, instruction set architecture, about Knuth, MMIX instruction set, about math notations. So thank you guys for coming. Have a great day. Bye.